Hello everyone, and welcome to the video lecture on the logic of hypothesis testing. This video lecture will be most helpful to you if you have already read the text lecture in this unit, because the video lecture, like most of the video lectures in the course, focuses on the big general concepts and not on all of the little details. So, as you have hopefully read in the text lecture, remember that all hypotheses tests can be expressed as a fraction, wherein the numerator is going to calculate the differences between means that we believe are because of the independent variable, and that the denominator of all hypotheses tests is always going to be referred to as error. Error is not a mistake, but rather error in hypothesis testing are the differences between the means we believe are there because of many different things, but not because of the effects of the independent variable. In this unit and for the remainder of the semester, you will be reading research scenarios. Research scenarios let you know what it is that a researcher has done. By reading the research scenario, you will have to be able to answer some questions. For example, which hypothesis test do you need to use in order to analyze the data that is presented to you in a given research scenario? And one way to make the decision about which hypothesis test is appropriate is to become clear on what means you need to compare. So let us read this research scenario. The population for 2-year-olds' weights is known to have a mean of 26 and a standard deviation of 4. A researcher hypothesizes that providing lots of touch to premature babies will have an effect on their weight. The researcher takes a sample of n equals 16 premature babies and provides lots of touch to the babies. When the babies reach 2 years of age, the researcher measures their weight and finds that the sample mean is equal to 30. And the question is, can the researcher conclude that the treatment, the independent variable, the touch, had a significant effect on the weight, the dependent variable? Well, looking at this research scenario, you should note that the means we're working with is a population mean and a sample mean. So the researcher is going to take a sample of babies, give them lots of touch. When they're 2 years old, the researcher weighed all those babies and found that the sample of babies had a mean weight of 30 pounds. So we want to compare the population mean of 26 for all the babies who were not touched to the sample mean of 30 for the babies who were touched. So what means do we need to compare? Well, we need to compare a sample mean and a population mean. When that's the case, we have a choice of two hypotheses tests. We can do a z-test or we can do a single sample t-test. To make the decision between this test or this test, we can ask another question, and that is, do we know the population mean? And if you refer back to the scenario, we do know the population mean. I'm sorry, not the population mean, the population standard deviation. The question is, do we know the population standard deviation? And the answer is yes, we do know it. It's given and provided right here in the scenario. So if we do know it, if the answer is yes, then we'll do the z-test. If we did not know the population standard deviation, if the answer were no, then we would do the single sample t-test. So clearly, or maybe not so clearly, but from the scenario, we know, or we should be able to know with some practice, that we will need to run a z-test, which is the test that we focus on in this unit. Another thing that we need to know after we know which test we're doing, in this case we know that we are doing a z-test, we also have to know whether we're going to run a directional one-tail hypothesis test or z-test, or a non-directional two-tail z-test. And how to figure that out is to be very clear on what our hypothesis is. If we go back to the scenario, you can see that the hypothesis is stated rather clearly, right? It says a researcher hypothesizes that providing lots of touch to premature babies will have an effect on their weight. So the hypothesis in a very simple form can be written as providing touch will have an effect on weight. Notice that the researcher is not predicting whether weight will increase or decrease, but simply that providing touch will have an effect on weight. When that's the case, we would call that hypothesis non-directional, and we would use what's called a two-tail test, which means that when we set our critical region, which I'll discuss a little later, we will be looking for an effect in both tails. That's why it's called a two-tail. If the hypothesis, however, were directional, it would read something like providing touch will increase weight. Notice the difference, right? Here, the researcher is hypothesizing that providing touch will have an effect on weight. There's no direction of that effect. Whereas if the hypothesis read providing touch will increase weight, clearly the researcher here is hypothesizing that the effect on weight will be in a specific direction. That is, that weight as a function of the touch will increase. Therefore, here we have a directional hypothesis, and we would look for an effect in only one tail. And in the other direction here, if the hypothesis were that providing touch will decrease weight, notice that now the prediction is in the other direction. It would also be a directional hypothesis, and we would only be looking for an effect on the left-hand side of the distribution out here in this tail. So remember, there are means in the middle here, right? So if the hypothesis states just an effect without a direction, then it's a non-directional hypothesis, and we need a two-tail test. We would look for effects in both tails. When the hypothesis is directional, either an increase where we expect that the effect of the study will go in this direction, then we would look for an effect only on the right-hand tail. But if the hypothesis predicted a decrease in weight, a moving away from the mean in this direction, then we would be looking for effects only in the left-hand side of the distribution, out here in this tail. Once you know the test that you have to run, then you are ready to begin the four-step process of hypothesis testing. Here, what I want you to see is that if you had already run this hypothesis test, your hypothesis test would wind up looking like this. You would begin with step 1, where you would name the hypotheses. There are 2 of them. Then in step 2, you'd set a critical region. In step 3, you would do the math. And in step 4, you would make a decision. After you completed the 4 steps, you would write up your results. In order to be able to carry out this 4-step process and to write up results demands that you understand how to do each step, which is what we focus on the remainder of this video. So step 1 is to name the hypotheses, and there are 2 hypotheses that you would name in step 1. HO is referred to as the null hypothesis. The null hypothesis states that nothing happens, that the touch will have no effect on weight. The researcher's hypothesis, statistically noted as H1, states that touch will have an effect on weight. So the researcher's hypothesis is a positive hypothesis, meaning it will always say that something will happen, whereas the null hypothesis is the nullifying of the researcher's hypothesis, and so the null hypothesis always predicts that touch will have no effect on weight. So again, step 1 is to name the hypotheses, and how you would do it is you would read your research scenario, which I have reprinted here, and you'd have to locate your hypothesis. In this case, providing lots of touch to premature babies will have an effect on their weight, so that the researcher's hypothesis would be that touch will have an effect on weight, and then the null hypothesis is the nullification of that, which would be touch will have no effect on weight. When we run a hypothesis test, when we do the statistical analysis, we test the null hypothesis. That is, we run an analysis to see the probability that touch will actually have no effect on weight. That is a difficult part of the logic of hypothesis testing, but hopefully between this video and your reading you will have, or at least you will come to some understanding of it. So again, step 1, name the hypotheses, and there are always 2 hypotheses you're going to name, HO and H1. If we look back on the previous slide, if you were going to write out step 1, it would look like this. You would write the null hypothesis, HO, touch will not have an effect on weight, and then you would write the researcher's hypothesis as H1, touch will have an effect on weight. Once you've done that, you've completed step 1, and you can go on to step 2. Step 2 is setting a critical region. Of all the steps, perhaps this is the most difficult to conceptualize. So let's first define what a critical region is. Remember that in the last unit we talked about distributions, right? This is a symmetrical distribution, and you may remember from our discussions on probability that the high probability outcomes are located in the middle of the distribution, and the low probability outcomes, remember those extreme scores, they're located out here in the tails of the distribution. So, by definition, a critical regions, or rather, let me say that again. Critical regions are, by definition, low probability outcome areas of distributions. So these low probability areas of the distribution are what's referred to as critical regions. So in order to complete step 2 and set a critical region, we would have to divide a distribution of all possible sample mean outcomes into areas of low and high probability outcomes if the null hypothesis HO is true. This statement is very difficult, in my opinion, to conceptualize. So let us take it a piece at a time. First, again, critical regions are low probability areas. And when we want to set a critical region, what we want to do is divide the distribution into areas of high probability and low probability. But in hypothesis testing, we have to use a different distribution than those which we've seen up to this point in the course. And the distribution is called the distribution of all possible sample means. And in order to give you an idea of what that is, I want to refer back again to information that we covered in the last unit. You will come to see how important it is to understand what we cover as we go along, because as we continue to progress throughout the course, the new learning requires that you have a good understanding of what has come before. So perhaps you remember in the last unit when we were working with z-scores that in a distribution you would have a bunch of x-scores, right? The distribution would have a bunch of x-scores in it, and that each x-score would have a specific location. Remember that? Each x-score would have a specific location, and the location of any x-score is provided by a z-score. And the idea was that a z-score works like a GPS to locate any one x-score, so that when you had an x-score and you wanted to know its precise location, you calculated its z-score. And you may also remember that z-scores of 2 standard deviations from the mean, whether 2 standard deviations above the mean or 2 standard deviations below the mean, you might remember that these were the areas of the extreme scores, and that here in the middle we had the average or central scores. So that some x-scores are extreme or low probability outcome scores, and some x-scores are central and have higher probability outcomes. If you do remember that, then understanding this new distribution may be easier. This distribution is a distribution of sample means rather than it being a distribution of x scores, single x scores, as we worked with in the last unit. Now we are working with the distribution of sample means, and just like the x scores, every sample mean also has a location on a distribution. Each one of these sample means is located at a very specific point in the distribution, and each sample mean also has a z-score that provides its exact location. So whereas before, again, the z-score worked as a GPS to find an x-score, and you calculated those z-scores. Now the z is going to work like a GPS to find sample means, and you can also calculate a z-score for the location of any one of these sample means. And the formula looks a lot like the z-score formula that we used in the last unit, but now notice that in the previous unit, to calculate a z for individual x-scores, we got a deviation score between an individual x-score and the mean and divided it by the standard deviation. Now we are going to look for the difference not between an x but a sample mean. So the z formula is going to be the sample mean minus the population mean divided by what's called the standard error, which I'll discuss later in the video. Right now, what I want you to see is that this is a distribution of all possible sample means that we could get whenever we take one sample from any one distribution, and that each sample mean has a location that is provided by its z-score, and here the z values work like a GPS to locate any one of those sample means. And just like with the x-scores, out here in the tails of the distribution, we're going to have the extreme sample means with low probability outcomes, as we will have the extreme sample means out in this tail, also with low probability outcomes. And here in the middle around the mean, as you might remember, the sample means that are located here have higher probability outcomes. So, setting a critical region on the distribution of sample means. So step 2 is to set a critical region, and we have to set that critical region using the distribution of sample means. And so the question becomes, given that we have to separate this distribution into areas of high probability and areas of low probability, just where are we going to put our dividing lines that will separate these two areas, the high probability area and the low probability area? So are we going to maybe put the lines where these two blue lines are, or where the darker two blue lines are? Or are we going to separate out the low probability area way out here in the tail where the green lines are? That question is answered by choosing an alpha level. Here is the statistical notation. Alpha, the Greek letter word alpha, is, interestingly enough, right, the statistical notation for our alpha level. And by convention, alpha levels are 0.05, 0.01, or 0.001. And what this means is that if we choose an alpha level of 0.05, then what we're saying is that we will allocate 5% of our distribution of sample means to critical region or low probability area. If we chose an alpha level of 0.01, that means that we would be allocating only 1% of this entire distribution to a low probability area or critical region. And if we chose the smallest alpha level, 0.001, then that would mean that we are allocating only 0.1% of the distribution of sample means here to low probability outcome or critical region area. Here you can see that if we were going to choose an alpha level of 0.05, it's blocked here, but what it says is alpha level equals 0.05. If we were going to choose an alpha level of 0.05, then our critical regions would be set here, the two here that are closest to the mean. If we were going to choose an alpha level of 0.01, we would move the critical region to the right and to the left. And if we were going to use an alpha level of 0.01, we would move the critical region, or rather, let me say, we would move the line that is going to separate the low probability area from the high probability area way out here in the tail. By convention, the alpha level most often used is 0.05, and the alpha level of 0.05 is the only alpha level that we will use in this course. But you should be aware that there are two others. So, setting then the critical regions for the z-test. We're still working on step 2, setting the critical regions or the low probability areas. We have to divide our distribution into areas of high and low probability. And we are working with the z-test. And when you are conducting the z-hypothesis test, the critical regions will always be as they are noted on this slide. And at alpha 0.05, if we were running a non-directional z-test, a two-tail z-test at an alpha of 0.05, then our critical region would always be set as you see here. We would divide this distribution into areas of high probability and areas of low probability by allocating 5% of this distribution, because it's alpha 0.05, allocating 5% of this distribution to low probability areas or critical regions. Because we have a non-directional test, a two-tail test, what we would do is we would divide our alpha level of 0.05 or 5% such that 2.5% of our alpha level would be on this tail, and 2.5% of our alpha level of 0.05 would be out in this tail. And so notice that the tails out here, everything to the right of this line and everything to the left of this line, these are our critical values that are separating low probability from high probability. And what this 1.96 and this negative 1.96, these are z-scores. Remember, z-scores locate very specific points on a distribution. So 1.96 is the z-score where you see this line right here, this point of the distribution, and this z-score, this critical value of 1.96, separates the top 2.5% of the distribution from the rest of it. Likewise, on this side, because now we're to the left of the mean, we have a negative 1.96 z-score, and that marks the exact location that separates out the very bottom 2.5% of the distribution. So again, for a two-tail test, alpha level of 5%, we separate the top 2.5% and the bottom 2.5%, And out here in the tails, these are what we call the critical regions, our low probability outcomes. And we define low probabilities as probabilities that are less than our alpha, probabilities that are less than our alpha. Again, out here in the tails, to the left of this line and to the right of this line, marked by these z-scores, this out here is what we refer to as critical region, low probability outcomes. And here, all the scores around the mean and all those that extend in either direction, but between these critical lines, these would be the high probability outcomes, probabilities that are greater than your alpha. If we had a directional hypothesis, for example, touch will decrease weight, then we would put our alpha level, our critical region, all on the left-hand side of the distribution, because if we had a directional hypothesis, again, that touch would decrease weight, then we would expect to see the effect to this side of the mean, and we would look for the effect here and only here. And so the z-score that separates out the full 5% of the lowest part of the distribution is a z-score of negative 1.65. If the hypothesis were directional, but in the opposite direction, say the hypothesis was that touch will increase weight, then we would be looking for a direction that would be in the direction of higher than the mean, right? Touch will increase weight, so we would be looking for the effect on the right hand of the tail, and we would put our entire alpha level, 0.05% of the critical region, entirely in the right hand tail, and the z-score that separates the top 5% of the distribution is positive 1.65. So at the end of all that, step 2 again is setting a critical region, and we're going to set a critical region for a non-directional test, a two-tail test, because remember, our hypothesis is that touch will have an effect on weight. There's no direction in the research scenario that we started with. So for our step 2, we would have a distribution of sample means, and we would go ahead and separate the distribution into areas of high probability outcomes and low probability outcomes by drawing these two lines in the tails of the distribution and marking that location with z-scores. A positive 1.96 z-score on this side, and on this side, although the negative isn't there, this would be a negative 1.96 z-score. Now, importantly here is that when we set this critical region, we are setting it in a way that demonstrates what we expect, our expected probability outcomes if the touch does not have an effect. That is what is meant when you read high probability outcomes if HO is true and low probability outcomes if HO is true. If HO is true is the same as saying if there is no effect, right? Because HO, the null hypothesis, states that there is no effect. So if HO is true, then it is true that there is no effect. When we set up this critical region, what we're doing is we're saying, hey, I have a sample of babies and I'm going to give them some touch. And my hypothesis is that touch is going to have some effect on weight. And if we do see an effect from weight, if we do see an effect from touch, if touch does have an effect on weight, then there is going to be a very low probability of particular outcomes if indeed the touch does not work. And the same if we find a outcome that falls in this critical region, right? There's going to be a very low probability that HO is true, or a very low probability that the touch did not work if our final outcome lands here. If our final outcome lands in the high probability area, that would mean, notice that if we land here, then there is a very high probability that the null hypothesis is true, meaning that there is no effect, that the touch did not work. So let me just try to say that again, because I understand that the logic of testing the null hypothesis, testing that the independent variable does not have an effect on the dependent variable, that touch will not have an effect on weight. The idea would be, again, that we set a critical region based on testing the null hypothesis. We are testing that the touch will not have an effect on weight. And so we are saying that if the touch does not have an effect on weight, there is a very high probability that our analysis is going to land here. And if the touch does not have an effect on weight, there is a very low probability that our statistical analysis outcome is going to land in the critical regions. Then, once we've set the critical region, we can go ahead on to step 3. And step 3 is doing the math. And while some students in statistics fear the math, quite frankly, it's almost a relief to get to the math part. But at this point in the video, I'm going to stop here, and I'm going to continue this lecture on the next video.